Hello, hello, hello. Can I hear myself? Yeah, cool. And I'm pretty low on the volume, so that sounds about okay. Cool, okay. Um, yeah, so it's late, I'm tired, so it was the perfect time to do some really, really hard stuff. Um, Jokes aside, by the way, when I'm talking about things in any of these videos, I'm not sure if I'm right, so, if for some reason someone's watching and you see something wrong, you have to tell me, right? Because I have no idea. I'm learning, right? Live learning. So, yeah, my apologies. And I always like watch over my video, and I'm like, oh man, what did I say that for? And da da da. So, I am aware, but it's not no point in always catching them. But yeah, just tell me if there's something that's dumb, because I'm pretty sure I say lots of dumb things. This isn't Greek, right? So starting off with Greek lesson. Yeah. Oh wow, we've broken the dials again. Actually, let me just close this door as always. Set the mood maybe with a bit of a better light. Let's see. Set the mood. What we got today? We're thinking we're on kind of an orange at the moment, so let's go. Let's go. Oh wait, how do I do this? Oh, I don't know how to do it. Ha. Maybe I don't know. There. How's that looking? Maybe there. It's got a little bit too much blue in it, maybe. Oh yeah, we're feeling that. Okay, cool. Right. So yeah, Greek. Let's do this. I guess we'll go with this one.
Στο σινεμά.
Sto cinema. So this is sigma, so that would be that one.
Στο.
And the cinema with the N and the M.
Σινεμά.
Cinema.
Ναι, Βαρβάρα.
Ne is yes. Va
Ναι, Βαρβάρα.
Vavara. That must be a new word. Vavara. What wonder what that means. Vavara. Yes. Vavara. I don't know.
Βαρβάρα.
Oh, it's a name. I see. Yes, Varvara. Okay.
Βαρβάρα.
Fara. Okay, got you.
Στο μίνι μάρκετ.
Sto
Στο.
mini
Μίνι.
market.
Μάρκετ.
Yeah. At the store. At the. Yes. Nay.
Ναι.
Varvara.
Βαρβάρα. Το ροζ βάζο.
To
Το. Ροζ.
rose. What did you say again?
Το ροζ βάζο.
Vaso. Vaso.
Βάζο.
So the pink vase, whatever it is. The pink cinema. To rose cinema. Cinema. To
Το
rose
ροζ.
cinema.
Σινεμά. Άννα και
Cinema.
Μαρία.
Cinema. What did she say?
Άννα και Μαρία.
Anna
Και.
and Maria.
Μαρία.
Yeah. Maria? Nay. Katarina. Okay, sorry. Maria?
Μαρία. Και.
Okay.
Κατερίνα.
Katarina. Katarina. P for the R.
Είναι το
Yep.
νερό.
Ine? It's the water. Or maybe it's with, I can't remember.
Είναι.
It is the water. Ine.
Το ροζ σινεμά. Το.
To rose
Ροζ.
cinema.
Σινεμά.
Cinema. Okay.
Καρότο με ρύζι.
Carrot. Me. With rizi, rice. I'll always forget
Ρύζι.
that one. The U for the E. Rizi. At the mini market, which is ine. Apparently it's not. Sto, that's right.
sto,
Sto, mini market, mini
mini, market,
market, market. Sto, mini market.
Carmen το νερό,
Carmen, Carmen, the water. Carmen, okay. Carrot and water. Carotto,
καρότο,
uh,
και,
que, nero.
νερό,
Okay. And the carrot, carotto.
καρότο,
Oh, do
το, καρότο,
carotto with is um
και,
que, nero.
νερό,
Me. Okay. Me,
με, νερό,
nero. Do carotto. Me is with nero water. Okay. Me is with. I'll forget it again. Need to practice this more. That means I've got to do more of this science stuff, right? Science stuff. Okay, cool. So that's over and done with. Let's close that down. What are we doing? This is the wrong thing. How do I get my hand back? There it is. So 24. Yeah, so we were looking at trying to get some data for getting some data for a wave function. I remember watching I think 3 lectures from the MIT online learning courses. Maybe Adam or Andy something. Um, they're amazing. So he was talking about the double slit experiment and how weird it was. He used an example of a monkey in a box, and you send a color or a uh, hardness or softness into the box, and the monkey knows which way to send it out, and various probabilities come out of it, and then some of the assumptions that you would make would be wrong because quantum's weird and all that stuff. So I watched that. I'm not sure it all sank in, and it certainly got heavy with um, kind of prerequisite knowledge that I didn't have. So I think I was on 804, which is one course at MIT, I guess, and he was talking about things in 802. So clearly I need to watch more stuff to understand that. But it was so interesting because I saw another video, I think it was just today or yesterday, that Sabine Hossenfelder, she was talking about the double slit experiment, and I think maybe she was talking about Bell's inequality theorem. It wasn't quite what I needed, but it was very interesting to talk about kind of real. Wait, no. I think I went on to watch a video that I'd already watched about real about imaginary numbers. So I just thought it was interesting because it's kind of the topic, and I'm guessing that YouTube has some kind of algorithm running that tries to help me out here. Um, Needless to say, still haven't really got to the crux of the matter. However, Sabina did say, I'm sorry if I'm mispronouncing her name, but she did say that you can get a real number out of the Schrödinger equation, which denotes what I assume was a probability, right? A probability distribution. Um, Now, I don't quite understand that because I would assume that probability distribution required like positional data along some x-axis, maybe a complex plane, but or maybe not, maybe just x and y. I don't know. But the weirdness was maybe I've misunderstood. Maybe that the number that comes out is some um, frequency of a wave or something. Um, but then you would imagine, well, if it was a frequency of the wave, what was the amplitude, etc. So um, yeah, I wasn't quite understanding it. I probably should have watched it several times. But I guess we're going to push ahead with that stuff again. Um, Leading on to just thinking ahead. Not that it ever really matters because I never go with it anyway. But then I would like to start to figure out some programs that I could write, whereby I put in a wave function, I get some probability distribution out or whatever it is, and then I can start to think about how I can visualize that in Unreal Engine. Um, Obviously, once I do that, I can start to intuit interactions between between particles. But yeah, let's start with getting some actual data back. So um, I'll just take it easy, you know. Oh, it's my birthday today, so yeah, just take it easy, try and enjoy myself, not overthink too much, and I'll just go with the flow. And sorry if I'm an idiot throughout it. So here we go. Um, let's go look at all the tabs that I had. Oh yeah, that's right. So I was looking at some kind of paper here. This isn't a paper. This is like a tutorial thing, isn't it? Path electrons, alpha particle. Yeah. Field ion microscope, scanning tunneling microscope, stum, hydrogen atom. That's a beautiful picture. I love that. This is so interesting. This. Um, yeah. I'm just trying to figure out if this is worth actually reading through. Um, it probably is because it does seem to be going into these ideas of probability density. And check this out, right? It's got those numbers that I've put into my own program. Interesting how how it's gone down that route and seem to be following some kind of trajectory, which is good, naturally. Where n was the principal quantum number, I think. L was the angular. I don't know if it was angular momentum. It says angular. I don't know what that really refers to. And m was the orbital something or other. See if it says here. I think it says in my notes. I think I did this last time as well. That's why episode 16 was up or something. 18 maybe. Um, Magnetic quantum numbers. Uh, but I'm still sure that one of those was to do with the orbital, like, stats. Well, I definitely wrote that down somewhere. Can you see any of this? I have to make sure you can see stuff. Kind of. Um, Maybe I didn't write it down actually, it's possible. I'm not, by the way, I'm not flicking this so weirdly, it's OneNote doing it. So I think this is uh, and so now we're going into machine learning, I think. Yeah, okay, and this is some of the okay, so gone back too far. Um, Let's just remind ourselves what that is. Ooh, forbidden. You don't have permission to look at this anymore. Ooh, okay. That's the problem with linking into sites, eh? Oh, that's a shame. That is a real shame. I wonder why they've done that. Maybe it was reference from Google. And they didn't mean for it to be open. Okay, fine. Let's moving on. Might as well delete that, I guess. Well, well, maybe this is the. Maybe that. Here we go. Here we go. But I remember this. Okay, you can't see it, but it's not worth looking at. Okay. You know, that's a great note. Describes the probability of position in a three-dimensional coordinate system. NLM. So that's what those numbers are for, eh? There you go. Yeah, I thought so. L is the shape, M is the size, and N is something. Man, I wish I'd written this down. Ay ay ay. The three quantum numbers that describe an orbital are integers 0, 1, 2, 3, and so on. The principal quantum number cannot be 0. The allowed values of n are therefore 1, 2, 3, 4, so on. The angular quantum number can be any integer between 0 and n minus 1, and the magnetic quantum number can be any integer between minus L and plus L. Great, but what does it mean? I remember this being something I looked at. Uh, nope, 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 nope. But this, I think, is that good link that has lots of cool stuff on it. Yeah, it is. So I think it says it here. Um, the principal quantum number n describes the size of the orbital, describes the shape of the orbital L, and m uh, the orientation in space of a particular orbital. Yes, okay. So let's try and find once again I'm going to close all this stuff. No, I'm just going to look for it first. So that's fine. Hydrogen, fine. Let's keep that open. Actually, that's going to be worthwhile. Ground state, overline. Oh, what did that mean again? Uh, in mathematics, line segment. It's a part of a line that is bounded by two distinct endpoints and contains every point on the line that is between its endpoints. A closed line segment includes both endpoints, while an open line segment includes both endpoints. A half open line. When it is not possible to format a number so that the overline is over the digits that repeat, one overline character is placed to the left of the digits that repeat. And the overline is used to indicate a sample mean. So mean is the average value of x sub I. Okay, so that's what those lines mean. In physics, an overline sometimes indicates the vector, although boldface and arrows are also commonly used. Okay, cool. Good. Next one. Heraclitean. That was from that paper, I think. Microscopy. Quantum microscope peers into the hydrogen atom. Um, this looks really interesting, actually. He says, closing it. Okay, cool. Balmer series. Can't quite remember what that was about.
This came back from a search.
Hi Google. Um, this is that paper. Electron position, exponentiation. Okay. Okay, rational number. Yep. Monomial is roughly speaking a polynomial which has only one term. Okay, that makes sense. Algebraic equation, ring, field, complex number, and Schrödinger equation. Okay, so these are looking good now. Yeah, let's do some searching then. So, um, let me think. Data for hydrogen, electrons. Get phase, ion, energetics data. So ions are the part where the electron is not in balance with the proton, I think. I think so. The phase of something is it the frequency of a wave? Phase versus frequency of wave. Are they synonyms? Rate at which the wave propagates in any medium. The phase velocity of a wave is the... Okay, so that's different from phase though. Phase of wave. Wave phase is the offset of a wave from a given point. When two waves cross paths, they either cancel each other out or complement each other, depending on their phase. These effects are called constructive and destructive. The word phase is used to describe a specific location within a given cycle of a periodic wave. Specific location within a given cycle of a periodic wave. Okay, that makes sense from the last diagram we just saw as well. Don't want to... This is probably really helpful though. Oh, who cares? I'm
Talk
sure it'll
about
be fine.
wave phase. Wave phase is kind of a strange idea, but it turns out to be very, very, very useful and not really that difficult once we understand what it means. The word phase is used to describe a specific location within a given cycle of a periodic wave. So when I look at a periodic wave, here I've got two cycles. Now, point A, point B, point C, point D, point E, and so on don't represent the same place within the cycle that goes from A to G. They just don't. So we want to be able to talk about the relationship between A and other parts of another wave that later cycle that are kind of the same thing as A. So if it's the same thing, we say that they're in phase. So let's look at this. All right, so we got point A. What other points are in phase with point A? Well, point D is at the same place, but the wave's not doing the same thing. Here the wave's going up, here the wave's going down. So A and D are not in phase. They have different phase, all right? What about, well, it's obvious that B, C, E, and F. What about G? Well, at G, we've got same place, doing same thing. So A and G will be in phase. All right, let's look at point B. Point B is an easy one because it's a peak. Anytime you're at a peak, there's only one place in the wave where you can get to that peak. So any place you're at the peak, you're in phase. Good enough. Obviously, F is not, and it's kind of the opposite. All right, we'll talk about that in a minute. What about point C? Well, for point C, we've got
J.
two possibilities, H and J. Now, with H, it's at the same location, but again, it's not doing the same thing. So C and H are not in phase, but C and J are. All right, fairly simple. Trust you understand it. Just look, same place, doing same thing, in phase. All right, so why do we care about this? Well, a wavelength can be defined as the distance between any two consecutive locations that are in phase with each
Okay,
other.
that's good.
So that's kind of nice.
Awesome.
It means I don't need a crest and a crest or a trough and a trough. I just need phase, same phase. Done. Wavelength.
Legend.
What if they're out of phase? If they're out of phase, we'll use some trig to describe how far they are out of phase. So just like our standard sine and cosine graphs, we're going to take the whole wave as being 360 degrees. Or if we're using radians, we'll use 2 pi. But let's just go ahead and work in degrees for now. So what about A and B? They're clearly not in phase. So how far out of phase are they? So the question, let me rephrase it, is how far do I need to go inside the wave to go from A to B? All right. Well, the easiest way to look at this is as a fraction of the wavelength, which is really what phase is doing. So the wavelength is all the way from here to here. Now, half the wavelength is that, so this would be a quarter of the wavelength. A quarter of 360 degrees is 90 degrees. So we would say that A and B are 90 degrees out of phase. All right? What about A and C?
Okay.
Well, A and C are crest and trough. Now, in this case, it's a whole half wavelength out of phase. So we would say 180 degrees out of phase. Now, A and C are actually opposites in some sense. So instead of saying 180 degrees out of phase, sometimes people say they are completely out of phase. All right? A and D. Well, here we got to go all the way here, then this whole thing. So we could say 270 degrees out of phase. But we could also say A and E are in phase, and D is just 90 degrees backwards. So we could either say 270 degrees out of phase, or we could say 90 degrees out of phase in the other direction, or negative 90 degrees out of phase. All right, that's phase.
Cool. Okay, that was awesome. That's really awesome. Brightstorm.com. Go check them out for sure. Let me just note that because I like that a lot. What the hell was I doing though? I'm so excited about phases now. I can't even remember what I was doing. Yes, that's right. So gas phase ion energetics data. Right. Zoom in. It's weird when I zoom in. It's so difficult to read for me. I know that I have to do it for the actual viewing, but it's really weird. I'm so used to seeing it all in one place. See what we got here. So we've got some formula, H, molecular weight, great. Whatever that is, international units per ass, cockaroo, I don't know, what does it mean? EU pack, International Union of Pure and Applied Chemistry. Okay, so not ass pack. Um, Standard iron CHL. What's that mean? International Chemical Identifier. Oh, I did know that actually. Huh, I see that on Wiki sometimes. So it's International Chemical Identifier equals 1s, which is the shell position. That's the first shell position. I wonder what this is, or H. Wonder what that is. Copy to clipboard. Good. I'm sure that'll make sense soon enough, though. What does this version mean as well? Oh, a version of the identifier way of laying things out, I guess. Okay. So then you got the, what was it again? International Union of Pure and Applied Chemistry. So that one standard identifier key. CAS, what was that? Chemical Abstracts Service. Chemical information, okay. Richard's number, chemical structures H. This structure is also available as a 2D mole file. Ooh, that sounds exciting. Let's get that. Ooh, .gov, nice. NIST. MNIST makes me remember that for some reason. Downloads. Where are you, downloads? Downloads. Here we go. What is a mole file? How to? Oh, first of all, let me look at the file with Notepad++, because why not? Sure. What we got here? We've got, so if we go back to that site, this number does not match any of that. Okay, fine. One, that matches what? Oh, nothing. Okay, interesting. What's the 0? Because it doesn't have any headings. Copyright by the US, commerce on behalf of USA, all rights reserved. And a bunch of separated by what? 2 spaces. And then this is a tab? No. 1, 2, 3, 4, 5. Let me just show symbols here. Okay, yeah, just spaces. Right, let me also look this up then. So, how to read a .mol file, because it's not obvious. Anatomy of a mol file. Okay. Most connection table for. Let me just zoom this in. Most connection table formats contain one or more of the following: a list of atoms specifying the elemental identity of each atom, a list of bonds specifying the atoms that it connects, and the bond multiplicity. 2D or 3D spatial coordinates for each atom, sometimes measured, sometimes calculated, often it's not clear which. That's good. Should probably say counts of the number of atoms and bonds in the molecule. Attributes. Oh, I've got something itching my nose, really annoying. Attributes associated with atoms or bonds. e.g. RS configuration of a stereocenter dashed wedged bond. Ah, we know that. We've learned that here. Attributes associated with an entire structure, e.g. net charge. The mole file, a widely used a widely used chemical structure file format, contains all of these. Here is a mole file for benzoic acid generated by ChemDraw, which provides options to save or to copy sketches in this file format. ChemDraw. The following, okay, so the following figures illustrate the anatomy of a mole file. Version 2000 to be specific. The counts line, the atoms block, the bonds block, and the properties block. Counts block. I wish it was just JSON. Just label things. We've got all the space in the world now, right? Obscure and obsolete attributes. Number of atoms. Number of bonds. Is it chiral? And its file format. Okay, let's look at that. There we go. Number of atoms, number of bonds. Other shit. Is it chiral? And then the version. Okay. Atoms block, non-standard isotope, charge, valence, etc. Table footers often used instead. Bonds block. So this is pretty uninteresting because that is exactly what they've done here, isn't it? They've taken that data out. Well, in most places anyway. Okay, fine. So isotopologs, tritium, deuterium, isotope, isotopologs, logs, dialogues, isotopologs, information of isotopes maybe? No, questions of isotopes? I don't know. What's this etymology of that? What is that? I said what is. I meant to say what is. Coined by Sodi from iso, equal, plus Greek topos, place. Equal, place. What about the log? The term isotope is formed from the Greek roots from isos, equal, and topos, place. Oh, okay. Doesn't say. Doesn't say. But equal place, okay. So what does it mean by equal? What is isotopolog? Are molecules that differ only in their isotopic composition. They have the same chemical formula and bonding arrangement of atoms, but at least one atom has a different number of neutrons than the parent. Um, do I understand that? Not really. If I go to periodic table, see what they're trying to say. So I keep muting myself because I'm going to go to drink. Or I'm doing like a burp or something. um, Let me see. Tritium. I'm guessing. Well, let's not guess. Let's just ask. Tritium. Chemical. No. Tritium. Let's just do that. Symbol T or 3H? 3T. Highlight all. Okay, well, looks like it's not an element. It is a rare and radioactive isotope of hydrogen. I see. That makes sense. Um, let's see a little picture of it. It's got. Yeah, there's. I think that's. Oh, that's interesting. I did not know. That's a new lesson. That because this N, I'm assuming is the neutron, and so that is it neutrons add mass? Is that right? Neutrons are mass of atom, main mass. Mass to a proton. 1 AMU. Okay, I see. So it's equal mass of a proton. Um, so that's the heaviest, tritium, tritium, whatever it is. And it's an isotope because it's not equal, is that right? But equal to what? Because now I'm a little bit confused. Like I actually forgot that neutrons are even in the equation. So let me just define isotopes again. Funny how it circles back into chemistry, isn't it? Each of two or more forms of the same element that contain equal numbers of protons, but different numbers of neutrons in their nuclei. I see. Okay, that makes sense. Equal protons. Uh, by equal protons, I'm guessing it means with electrons. Forms of the same element that contain equal numbers of protons, but different numbers of neutrons in their nuclei. I mean, equal number of protons to what? I'm guessing this is a better write-up if I go through to it, but easy definition, yeah. One of two or more species of atoms of a chemical element with the same atomic number and position in the periodic table, and nearly identical chemical behavior, but with different atomic mass and physical properties. Atoms with the same number of protons but differ in number of neutrons. Same number of protons. Is this written by someone who has no idea what they're talking? I had no idea what they're talking about. How does it help anyone? Isotopes are atoms with the same number of protons but different in number of neutrons. I guess as the unit of being hydrogen, I guess it means the same protons, i.e. Okay, well, I guess it's not so important yet. So let's carry on. So these guys are the isotopes, and permanent link for this species. Use this link for bookmarking this species for future reference. Okay. Gas phase ion energetics data. Ooh. Close multiple tabs to the right. Data compilation, data compiled by, view reactions leading to, on structure unspecified. Ionization energy determinations. What is this saying? Oh, is it gone? Oh, I see. It's just taking me down here. Data compiled by view reactions. Okay, this is it, is it? Oh. Gas phase ion energetics data. Energetics data. Let's see what that means. That's not helpful. Okay, fine. So I've just searched that on Google and nothing comes up. That's interesting. So what the hell is it? Plus or minus. Other products. Electron impact techniques. Translational energy distribution and relative emission cross-section of excited hydrogen atom. Translational energy distribution and relative emission cross-section of excited hydrogen atom produced in electron chloroform collisions. 1982. NIST Chemistry Webbook. Okay, fine. Other data, reaction thermochemistry data. Yeah. Data at other public NIST sites. Atomic spectra. What does spectra mean? Define spectra. Sorry, one sec, just checking something. Settings. Yeah, okay. It is working. Okay, cool. I just looked at my thing and I was like, hang on, it's not working, but it is. Good, okay. So spectra is a band of colours as seen in a rainbow produced by separation of the components of light by their different degrees of refraction according to wavelength. Used to classify something in terms of its position on a scale between two extreme points. Okay. Lines holding, levels holding, ground states and ionization energies, impact ionization cross sections. So let's have a look at some of these. Lines with transition probabilities. Lines with level designations. What about that? What is this data? Why is this not super obvious to me? I must be an absolute idiot. NIST Atomic Spectra Database, Ionization Energies Data. Example of how to reference these results. Okay. H. Hydrogen. All spectra. 1 data row found. 1. Element name hydrogen. Isotope element. Sequence hydrogen. Ground shells. 1 shell. Ground level. 2s1 half. Ionization energy. Ionization energy. Uncertainty. Okay, this is good. So I've seen this a couple of times now, so it must be something. What is the unit EV in physics? Electron volt. Good. I'm gonna have to sit down and get in fidgety legs. Bear with me. Okay. Thing is, when I sit down, I just get sleepy. So, um, electron volt, unit of energy commonly used in atomic and nuclear physics, equal to the energy gained by an electron when the electrical potential at the electron increases by 1 volt. Ah, that's interesting. Equal to the energy gained by an electron when the electrical potential at the electron increases by 1 volt. Electron volt equals 1.602 times 10 to the negative 12. Egg. Or ERG, electronic rat gun. ERG unit. The erg is a unit of energy equal to 10 to negative 7. Okay, joules. It originated in the centimeter gram seconds system of units. Unit of energy equal to 10 to the negative 7. Weird, but okay. The electron volt equals, yep. Oh, so many things. Some uncertainty measured with the electron volt. Ionization measured in electron volts. References. Hudel. Let's have a look at this. Hudel. Energy levels of hydrogen and deuterium. This database provides theoretical value. That's interesting. Values of energy levels of hydrogen and deuterium for principal quantum numbers n1 to 200. Ooh. I wonder what happens when they go over Z. And all allowed orbital angular momenta and total angular momenta J. Momenta L and total angular momenta J. That looks like a forward slash. The values are based on current knowledge of the relevant theoretical contributions, including relativistic quantum electrodynamic recoil and nuclear size effects. Hyperfine structure effects are not included. Contributions that are only known for low N states have been extrapolated to highly excited states. Physical measurement laboratory. Search NIST. Okay, access the data. Um, Fundamental constants used in the calculations are taken from the CODATA 2002 least squares adjustment and can be found at the NIST Fundamental Physical Constants website. The changes that will result from using the most recent CODATA recommended values of the fundamental constants are insignificant for the theoretical predictions. Quoted uncertainties take into account uncertainties in the theoretical calculations, uncertainties in the fundamental constants, and covariances between the various contributions and input parameters. This interactive database allows a user to obtain individual energy levels and transition frequencies as well as tables of frequencies. Given the volume of the possible data, this website is designed to calculate the values on request. Access the data. This page provides access to the theoretical information used in the numerical calculation of the energy levels and transition frequencies given by this database. Theory and theoretical input data. These matrices can be used to obtain the data provided here. The energy level and transition frequency data may be accessed in a variety of forms as indicated by the links below. Theory and theoretical input data. The energy levels of hydrogen-like atoms are determined mainly by the Dirac eigenvalues. The energy levels of hydrogen-like atoms are determined mainly by the Dirac eigenvalues. Quantum electrodynamic QED effects such as self-energy and vacuum polarization, and nuclear size and motion effects. The theory and theoretical data needed for the evaluation of the energy levels in hydrogen and deuterium are summarized on this page. The energy levels and transition frequencies are calculated using the results of the 202 CODATA least squares adjustment of the fundamental physical constants. The calculation is least squares. Least squares. Okay. The calculation is based on the formulation described by U.D. Gentskura, Kotajigova, Lebigot, Moore, and Taylor in precise calculation of transition frequencies of hydrogen deuterium based on a least squares analysis. That was a lot. Okay, so matrices referred to in the above paper can be accessed from the Fundamental Constants website. Come on, mate. Where are we going? This reference on constants, units, and uncertainty. Most misspellings are okay. Yarr. Let's see what it comes up with. Ooh, okay. Nice. Is that by clicking a category below, display search by name, display by clicking a category below. Universal, electromagnetic, atomic and nuclear, physico-chemical, defined constants, non-standard something units, conversion factors for energy equivalence, X-ray values, frequently used constants, extensive listings. Oh my, these are images. Man, that's interesting. This is a government website. Okay, well, it's good that it's here, I guess. Haven't found anything yet, though. There's a lot of click-throughs. The contributions to the theoretical values of the individual elements' energy levels are summarized by Moore and Taylor. Largest creating contribution is the one-photon self-energy correction. This correction includes a non-relativistic Bethe the logarithm, which requires a separate calculation for each state. For states with principal quantum number n is less than or equal to 20, we employ the values given by Guth, Drake, and R.A. Swinson. Yep. The second largest QED contribution is the one photon vacuum polarization. The calculated data needed to evaluate this contribution is given by two photon corrections are somewhat smaller but still very important at the level of accuracy considered here. A summary of the... Have I missed something? Appendix A. Sheesh, guys. Is that the link I've got to bloody click? Alright, cool. Let's read this. Okay. SCO data recommended values of the fundamental physical constants. This summary is excerpted from the publication Reviews of Modern Physics. It describes describes the theory of energy levels in hydrogen and deuterium relevant to the... Okay. So, that's interesting, but this is not what I want. But finally I've got a table of data, which is lovely. Right, let's keep that open because it took bloody ages to find. Let's continue our search. So this is a governmental website about hydrogen atom, calorie-based units. Okay. Oh, we've got to get this better. This is not easy to dive right in. I'm at the wrong site. This is why. That is not the right site for me. Hydrogen's atomic emission spectrum. Atomic emission. Atomic. What does atomic mean? Define atomic. Relating to an atom or atoms. So where did I just see that? No, I can't see it. Oh yeah. Hydrogen's atomic emission spectrum. Atomic emission. That sounds good, actually. This looks really good, actually. Okay. Apart from that it's on a black page you can't see. Is that my problem? Have I done that? Maybe I've accidentally turned something on. Right, well, I guess I'll just double check my extensions. Add-ons and themes, extensions. Nope. Ad blocker. These aren't things I've got. Plugins. I guess the theme is causing it, maybe. Okay, well, it's kind of hard to see what these say. See if that works. Oh, it does. Great. Okay. Lines get doser and doser together, and eventually reach the series limit. Passion series, Balmer series, infrared partly visible, the Lying Man series, ultraviolet. I need to start, like, so the problem here is maybe I'm expecting something different. So this is what I'm expecting to see, right? I'm expecting to see something like episode 25, not something like episode 25, but something like this. Oh, actually, you know what? If I've got this as the center of an atom, right? That's just the center point. And you've got a thing called a neutron, right? So whatever this thing is, you'd expect it to have a center. So this is maybe where I'm going wrong. And let's imagine you have a proton close to it, and then I've got an electron over here, right? And this electron is doing some kind of weird gymnastics, and the protons is probably getting pulled by this and vice versa. So this will have some kind of orbiting and jiggling as well. And the neutron is negatively charged but has a mass. So that would cause some gravitational pull here, which also this proton might bash into it. I don't know how these work. So this is on a physical, like, particle idea of it. Now let's imagine, so yeah, so okay, so let's imagine they're all bashing around, right? So if this were true, if it was a particle, so only if particle, and by that I mean oh well, let's do this more clear. So by particle I mean like Newtonian physics kind of thing. Newton um based assumption. Newtonian based assumptions. So if I wanted to get some figures for these, so let's imagine there's a probability that it would be somewhere along this orbit. So you'd have the m value, no, you'd have the n value, the l value, and the m value. But this is angular, angular. The shape, size, and orientation. Shape, size, and orientation of electrons. Orientation of electrons, right? Okay, so that's three numbers to describe these things. So let's imagine we've got the shape of I don't know, let's say a shape is defined by an array or set of a set of vertices. So vertices could be described in three-dimensional space. So we'd have vertices where that is where V is, well, it'll be a vector, wouldn't it? So I could just put a vector, right? Oh, I can't undo now. Of course I can't undo. Why can I not undo? I can't undo anything. I don't understand this application at all. Anyway, so this would be V. Yeah, okay, that would be fine. Anyway, V. God, 1, 2, V, N, and we'll call this the shape. Because then, uh, yeah, because you'd imagine like having some kind of shape defined by, some points on a Euclidean space kind of thing, and you join them up, and then you take you'd integrate them. No, you wouldn't. You'd like just divide the line up basically, and then interpolate. That's right, interpolate. That's what I meant to say. To kind of smooth off the line or whatever. Let me just put that make a bit more sense then. Right, so let's imagine that that was a thing. And then you would have the size would be like, well, I mean, it could be a scalar, couldn't it? So size would be, so this is 1, right? Datum 1. Datum 2 would be size is equal to a, well, it'd be just one vector, right? It would be the S. Well, we'll just do that again. It'd be a vector. So that would be 1, oops, 1, 1, where this is X, Y, and Z. And then you'd have the orientation, which would be the same as this. So ditto of that, but orientation. That's not clear. But I just copy it, right? It'd be a vector, and that's fine. So then we've got our 3 kind of assumptions of what data might or should look like if it's going to be helpful to me, right? Now, let's imagine instead these are these waves, right? So that's that. Newtonian-based assumptions. Now these are wave assumptions. Wave assumptions. Okay. So let me redraw this. If we have this center and this got a this center is just a point, right? And no, that's the wrong assumption. So we've got this proton, neutron, and electron. So these are locations, right? And if this was a wave, can a wave, is it frequency? Wave is it? Wave is, this is a wave, right? This is a sinoid wave. So let's imagine this gives us, it's, okay, this is interesting to think about. So recording this with, I don't know for sure, I'm just going to say it and that'll be enough to drive me. We're recording this with electromagnetic analysis, right? Something like that. Whatever. And this is what the kind of readings are giving us. Electromagnetic waves. So how do we deduct position from such a thing? Well, we're pointing at it for one thing. So let's imagine our gun is here and we have this line and we're doing a reading here. So we know that this is 0, 0, 0, 0, right? Now as it goes past, at that point, let's say this is 0, 0, 0, 0, this is at 0 basically. I'm just trying to say that at 0 there is this wave, right? So we already have a position. So we can maybe say that this is the y value. This is wrong. So what I need to do is know how these things are actually recorded, don't I? Experiment to show position of electron. Let's just see how it works. Ah, now that's also right, because the standard model of elementary particles, that is, oh, so the electron is a base unit. So what's a proton made of? What is a proton made of? Up quarks and down quarks. Okay. Helium. One proton minus electron. As constructed, two types of elementary particles, electrons and quarks. Electrons occupy a space that surrounds an atom's nucleus. Each electron has an electrical charge of -1. Quarks make up protons and neutrons, which in turn make up an atom's nucleus. Each proton and each neutron contains 3 quarks. Each proton and each neutron contains 3 quarks. Okay, so proton, neutron, 3 quarks. 3 quarks. Okay. Protons contain 2 up quarks and 1 down quark. 2 up, 1 down. Neutrons contain 1 up quark and 2 down. 1 up and 2 down. Okay. The nucleus is held together by the strong nuclear force, which is one of 4 strong nuclear force. Nucleus is held together. This, you know what? I'll do another color. Oops. This is held together. How do I do that? Let's do this like a link. strong nuclear force. Nuclear. Which is one of the four fundamental forces. Gravity and electromagnetism are two others. The strong force counteracts the tendency of the positively charged protons to repel each other. It also holds together the quarks that make up the protons and neutrons. In addition to electrons and quarks, physicists have identified a number of other subatomic particles. Quantum physics describes the subatomic world as one that cannot be depicted in diagrams. Particles are not dots in space, as depicted in this feature, but are more like dancing points of energy. Yeah, fine. Dancing points of energy. But, I mean, point is a bad analogy there if you're not talking about dots in space. A dot in space is a point, right? Dancing points of energy. Yeah, that's not a good intuition builder, that, in my opinion. I'm trying to think of what my challenges are here. I wonder if, okay, so let me think about this. So if I've got, let's say I've got a uh three quarks of the proton and neutron. Let's look at the forces acting upon them. So if I had, let's say we had the proton here and a neutron, and this has no charge, right? No charge at all. So it has a mass, so its mass will exert gravity. So this is pulled to this with m mass. Now, a proton has mass as well. So let's look at the, okay, so hydrogen, proton mass. Do all protons weigh the same? There is a discrete set of masses and sizes for the proton and neutron. In practice, they decay from such states to their ground states, so the practical answer is all protons and neutrons are found in exactly the same size and mass. So what is the mass of a proton? Right, 1.6, right? So m equals 1.6, and that we'll call this m of n, which is wrong, but anyway, mass of a neutron. Neutron, it has no electric charge and a rest mass equal to 1.6. So that is the same. 6, 7. Oh, no, it's not the same. 6, 7, 4. 1.675. Well, you know what? I should just write it right. So m is equal to 1. M of n is equal to 1.67493 times 10. Well, that's confusing, isn't it? Times 10 to the 27. Okay. And let's do this one in blue. This. Oh man, let's do it in green then. This is m of p. P is equal to um that 1.6726219, okay, times 10 to the negative 27. So they're very similar. Okay, it's good. And then, okay, so that's that. And then we've got electron as well. And let's put that over here. And that's also going to be pulled to this. But actually, let's do the interaction between the proton and neutron first. Okay. Mass of a proton, mass of a neutron. What was this measured in? Kilograms. Kilograms. Just make sure that other one was kilograms. Kilograms. And then, what is the mass of an electron? I think it's like almost massless, right? Oh. Yeah, okay, because this is negative, so, and this will be kind of irrelevant at the moment. Okay, cool. So, what else is there? So, E equals mc squared, that's energy. So the energy, so F equals ma, mass times acceleration. So the acceleration comes from energy. So that results in a force. So so we almost need a speed now. So what is the speed of a proton? Protons are accelerated such that their mass energy is 7 TeV, roughly equal to 1.12 microjoules, macro, something like that. Wikipedia states that the protons then have a speed of about 0.9991 c. So c is okay. Let's just go in here then. I'll be right back. Just gonna get some water. Cool. And also just gonna do a blood test. Oh man, my whoops. I was perfect a second ago, and I had that trek bar because I was like, oh, I think I might be going down low, but nope, I was wrong. Small injection. Be good. Okay. I think I've only been high for about 30 minutes then, I guess. Something like that. Also do my long-term injection. Sorry, I'm diabetic. Okay, cool. So this is getting interesting, actually. Um, I'll revise my answer. Since my last answer was too specific and was deleted, you can start with an equation relating relativistic kinetic energy to velocity. For these types of problems where you can't use a calculator, you need to be able to estimate the order of magnitude of the quantities involved. Since you see that the answers each differ by several orders of magnitude, estimating each quantity involved to powers of 10 will generally suffice. You will want to find a way to write the quantity that you are interested in this case Vc, as something like okay. Protons are accelerated such that their mass energy is 7 TeV. Let's just find out what that is. Total enterprise value. Nope, it's not that. TeV physics. Electron volt. TeV is a unit of energy used in particle physics. TeV is about the energy of motion of a flying mosquito. Energy of motion. What makes the LHC so extraordinary is that it squeezes energy into a space about a million times smaller than the mosquito. TeV stands for tera electron volts. And what does tera stand for? Denoting a factor of 10 to the 12. Or 2 to the 40. 10 to the 12. Teravolts, okay. So 7 times 10 to the 12. Wow, okay. So, what's the speed of a proton? Let's go back. This is not it. How fast does a proton have to be moving? No. Do protons always move at the same speed? It's not correct. Electron and protons move at the same speed because the electrons move within the atom at different speed in its different orbit. So, do protons move um, at different speeds? They don't move with the speed of light, they move at nearly the speed of light, but slightly less. If one of the protons in the LHC raced the light ray would pull ahead by about 3 meters, 10 feet for us Americans. Ever seen that? Every second that the race lasted. Every second. Okay, do protons, what speed do protons travel at? Speed of the proton must be, let me and V represent the mass and velocity of the electron. Okay, so it looks like protons can go at different speeds. And a lot of this stuff seems to be about units. That's interesting. So no one cares about units. Goodness me. I don't care about units. Not yet. A lot of questions about that. Um, Alright, okay, well, fine. Fine, fine, fine. So, so if we okay, let's just imagine that the because I basically if this was moving a certain way and this was moving a certain way, we need to know like if you were to be able to put an energy on this, because I mean at the moment this is all the forces in it, right? So I need to add um that's bad news. Let me do this again. If I erase this and that and make this green, we'll call this P. And then I'm going to do, well, actually, not even good idea. Let me do that as that P, and then I'm going to do that as grey as well. N, and this will be um, V N, and this will be V P. Now, suppose it doesn't really matter what those values are. Interesting that we got those so easily though. Let's see, VP is equal to, doesn't matter, and then just put the other one down, VN is equal to whatever. Okay, so now we have an equation like, so the kind of, well, do we want a net force? let's do net force. We can change this after. So P's net force is equal to um, minus m of n plus or minus, because I'm basically VP in this case is going to be variable location, so plus or minus the vector p VP plus or minus the vector VP, and that's cosine or sine depending on, no, that's, yeah, that's right, so it's cosine and sine, so it'll be cosine that, then plus, and this, and that'll be as well, yeah, that should also be grey, plus or minus, but that also needs to be cosine, whoops, like that, cosine mn, then it'll be, okay, and then sine, right. So let's do that. So then plus, well, why did I do negative? That's because it's going to come, it's going to be, it's going to be pulled away from itself. So that's the notation of negative I'm saying. And then, whereas the velocity is going to be pushing, because it's always pulling away from it. So it's going to plus from its original location. So actually, I think this should also be plus. So I can just knock that off. That's fine. So I mean, this is always going to be positive then if it's going away. So let's just do that. Oh, hello, plus sign. Good. And then yeah, so we just got the signs of these. So sine of m n, and then the sine of plus the sine of m of n, and then v of p. Right. Okay. Fine. So okay, yeah. So I'm not sure that's right because I haven't ever done three-dimensional here. So let me think of this for a sec. No, it's fine. I'm getting the idea. So in this 2D graph, let's imagine particle physics is 2D at the moment. Then that would be about right. And then I've got the, some reason my n's gone. Then I've got yeah, I have to remember this is not paint. PF net. So that's the force that's being applied to what though? The net force of what? I guess it would be, I need to know its, oh my god, yeah, no, this is what I actually want to do here. it's a force. It's its gravitational force. So I don't care about anything but what it's pulling towards it. Now it's a negative charge and nucleus has no charge, but it does have a mass, so it will gravitationally pull. Then it's got this strong nuclear force as well. Oh, okay. Well, this is good. This is fun. I might need to think properly about this. Let's simplify this a bit, because all I want to know is I want to know if I've got this thing, how is it going to pull this? So I need a force. So what's the force? And I also need to know in what direction it's going. So yeah, because if it's but actually I just need to know its force. I just need to know its force. Now, its position is so its position is important because I need to know how far away this is, right? Because the force is going to be scaled by that. Scaled by, well, equals mass times acceleration. Acceleration is so any position is going to be force equals mass times position. So acceleration is what? Acceleration equals, I can't remember, m times, oh okay. So average acceleration is equal to the final velocity minus the starting velocity divided by the elapsed time. Speed equals, so speed equals distance over time sort of thing. Change in velocity divided by change in time. Yeah, okay. So velocity is speed, not position. So position comes from measurement. Speed is important because of the differential part of it. So I'm probably this is probably the worst video ever. No one's ever gonna watch this. It's so boring watching someone think. But yeah, I'm starting to understand now. So if if it starts at D1 and then ends up at D2, right? Um, let's delete this. So it's yeah, okay, actually more like this. So D1 is here, D2 is here. Yes, okay, that's better. So the change in D, or change in position, vector. Yeah, let's do that instead. P and it is equal to P2 take away P1. Oh my god, James, I hate myself. Oh. Okay. Oh, 9 minutes left on my birthday. How can I celebrate? A beer. Bear with me. A meal for two at 6.9%. So funny. That was my birthday present for my bro and his wife and his beautiful kid. Alright. I've never had this before. Oh, it's hazy. Oh yeah. Actually, this looks vicious. 6.9%. That is a vicious beer. It's like a pint of wine. Or very weak wine. Oh, it smells great. A meal for two. Ah, cheers. Here's to my birthday. Okay. Let's try this. Oh, my goodness, that's delicious. Oh, wow. That is utterly delicious. Wow. So cool. Phantombrew.com. Oh, that's excellent beer. Get one of those. Okay, cool. So that's what we've got going here. So if we've got the change in that means we can differentiate with force from one position to the next. And that needs to be in coordination with so maybe we should call this PA1, PA2, and then we need P B P B P P um let's just imagine this goes over here and this will be P B1 P B2, so this would be the change in vector, the change vector of, or the change in P, yeah, but this is this is a vector, right? So this will be B is equal to P B minus P B2 and 1 vector vector. Okay, so we got that. And then So then it's, what is it, speed equals distance over time, acceleration equals change in speed over change in time. So, is that right? I can't remember now. I think it was. Yeah, velocity, speed. You know what I meant. You know what I meant. Oh, really? Velocity. Good, okay. Therefore, therefore, this is all going to be over t. So if I do this, in fact, you know what? I've got a lovely way of doing this now. If I move this, whoa. If I instead move this over here, this will be over t, change in time, and this will be over change in time. Good. Mm. Oh, that's so good. And then, so that's now acceleration. So I don't need to demonstrate that. We just need to demonstrate it with that symbol. So let's get rid of that because that's obvious. And that's also obvious. So let's delete that. Good. And the acceleration of p, so acceleration of p, no, of, I can't undo. Doesn't let me undo after a while. Of a, and the acceleration of b. Now, acceleration is over time, and with speed, so that I need position though. So it's the positions are PA1 and PA2, right? So then I've got it. So then this is d, distance between distance of A and B. So distance of A and B is equal to A yeah, A minus B, right? No, that's not right. It's distance is measured with uh with Pythagoras. So it's going to be this. Which would be B y minus B minus, well, where's our 0 really? What do we class as 0? Let's class the middle of the interaction, no, that's going to be difficult. So we'd class A as, so A is equal to origin, and so it'll be B, B, Y, equals opposite, and then adjacent is equal to Bx, and then distance, which we're saying D of A and B, is equal to By plus Bx square root. Okay, so let's do that. DAB is equal to the square root of By plus B Bx where A equals origin. Okay, good. Something doesn't feel quite right about this, so let me just double check that. You still don't use this stuff much. Something like that, anyway. I think that's right. Because I've dropped, thing is I've dropped, it's, so this squared plus this squared is equal to that squared. So if I want to square root this, I need to square root this side, which would take, I would need to square root that, I need to square root that. So then I've got double things, and then, oh well, anyway, let's just go with what I know here. So this is squared equals squared and squared, right? Easy, done. So, I should be able to do this. It's ridiculous. Sorry, I do this stuff all the time. It's just ridiculous that I can't do this now. So this is the square root of this is equal to whatever. Doesn't matter. Okay, cool. So now I've got the distance. I've got the accelerations, and DAB will change as, or it could change if B or A are accelerating faster, and so that's an unknown where that location will be until acceleration of A and B are known. Now, what about the n because that is for, so this is for gravitational force, gravitational force. What should I just put on? Nothing. Cool. But then I need to know the force applied by the charge. So I've probably done the easy part. So now I need to know what the charge forces are. So how to work out force from charges. Force to exerting each other. Electrostatic force. Force. Da, 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 close that. Oh man, so many adverts. Okay. Oh man. Electrostatic force is the force two electric charges exert on each other. It operates according to Coulomb's law, which states that the electrostatic force between two charges is equal to the multiplication of the magnitude of the charges divided by the square of the distance between them. Ah, I'm in love with that beer. Oh my goodness, did that just delete everything I've done? Okay, cool. It did not. So, writing down Coulomb's law, let's do that. We have here, I guess. No, let's do it here. So it says multiplication of the magnitude of the charges. So you've got charge 1 times charge 2 divided by the square of the distance between them. Square of the C. Whoa, that's not C. C2 minus C1. Well, actually, let's just do C. Yes, I got it. C1, 2 vector. So let's call this A and B instead, and it's less confusing. Distance between them. So people experience this force every day through common electrostatic or static. Yes, this, generally we can equate to a minor nuance. However, electrostatic charges such as lightning can be quite powerful. Find the magnitude of the first charge, or Q1. So Q is the charges. So let me just get the actual Coulomb equation. Let's just see if I got this right. K is the Coulomb constant. They did not say that in the other one. Coulomb constant, the electric force constant, or the electrostatic constant denoted K, is a proportionality constant in electrostatics equations. In standard something units, it is standard international units. It is equal to, oh yeah, here we go, kilograms per meter cubed. So okay, let's go with the constant here then. Let's delete that, that's wrong. So it's K, oh, radius, yeah, of course, that's what you'd do. Yeah, that's good, I like that. Q 2 over R2, and that's the force. Coulomb. Cool. Therefore, our electrical calculation here, so electrical charge force is equal to DAB DAB but where's the charge come from? Oh god, that's the next question. Okay, charges. So what is a charge? Physical property of matter. No longer my birthday. I'm now officially a new age. Electric charge is the physical property of matter that causes it to experience a force. Physical property of matter that causes it to experience a force when placed in an electromagnetic field. The electric charge can be positive or negative, commonly carried by protons and electrons respectively. Like charges repel each other and unlike charges attract each other. Okay, I see. So this is going to be P, but the neutron has no charge, so it exerts no force. So a neutron has no force, right? Neutron charge. It has no electric charge and a rest mass equal to that. So it's just a gravitational force there at the proton level, not the quarks level. So we've got a little bit further to go there. Yeah. So actually so this is not a thing, right? Let's say something like no neutron charge, so no coulombic force. Okay, nice. I need to make this a bit neater now. But that is so this is a summary of forces between neutron and proton. Now, I think this is at a particle level, because if I now go into the two ups, one down, one up, two down, quarks, do they have their own mass? Now, I don't think they do. I think they're just energy because they are waves, right? So let's just double check that. Mass of up quark. So it does have a mass, okay. In electron volts. The mass is in electron volts. What does that say to us? So there is there's 9 different charges that I need to figure out here. So this is like sub. I need to do an up. So I'm going to do the neutron, lower n. Oh. So lower n neutrons, quark up, or let's do that. Up quark. Wait, what's the notation for up quark? What do the other people do? Okay, let's do that then. So n up quark, and then that's 1. N up quark 2, and n down quark 1. Oh, sorry. Okay, other way around. That will be D1, D2, and that will be with a P for proton. No, no, yeah, no, for protons up quark 1, protons up quark 2, and protons down quark 1. And then we've got to do 1, 1, 2, 3, yksi, kaksi, kolme, and then 1, 2, 3. Now that negates the previous thing because they are in fact made up of this. So you would hope that the answer to my last one was roughly, well, no, you'd hope that it's precisely equal to this equation, but then again, we know that you can't make them equal to each other, and I wonder if that is the problem with quantum and gravity. I doubt it, but could be. Because you say that not equal to each other. Regardless, that is about the gravitational part, right? So I do all of that for that as well. Fine. But then I need to do the forces between the electron and the proton, which is going to have gravitational, but also it's going to have charges because it's negative and positive. So let's go ahead and do that. And let's also summarize what this is. So quarks and their gravitational forces. 1. Bam. Okay, 1's done. 2. Let's do the next one. 2. You probably can't see any of this, but I think actually I can make this a bit bigger now. In fact, I'll make it the whole screen because I think I know what I'm doing. So let's draw our diagram again, and we're going to do. This is a proton. And did I say proton was the origin? Where A equals origin. So let's not confuse myself here. Well, actually, so because this applies to everything, so I kind of generalized the problem here. Where A is origin. So let's say gravitational forces plus coulombic forces. Okay, let's move this little doozy down. Let's put a little thingamajiggy-bobby there. And then let's go for broke. So this is going to have a charge that comes from what is charge of electron and charge of proton. Okay, and symbol for charge is Q, I think. Q. Okay, so we're going to call this, well, this should be grey to start off with anyway, P and E. So we're going to say this is P Q, P Q, and this is E EQ. But they repel each other. So it's actually the other way around. This should be PQ because P is, because this charge is pushing away. No, that's right. That's right. So that's pushing that away, and that's pushing that away. No. I was right the second time around. So let me do that again. So this is P, and this is E because they attract each other, right? I'm an idiot. I said I'm an idiot. Okay. Wow. Um, and then the distance is R. Oh, that's a good point. I should also denote this R up here to stop being so confused in the future. Let's denote that with a nice, well, DAB. So let's scrub that out and call it R. And we'll do this as R as well. But it's the same color. This can be too confusing. Let me do a pink, a purple. Purple sounds good. Add one here, can we? Nope. Purple. No, it's going to be too... Ooh, yellow. Ooh, light blue. Ooh, this one. Let's do that one. Cool. Yeah. So if I just call that R there, scrub that out, call that R. And that's going to be R. And then this will be R. Oh my god. Okay. R. Okay. So now we've got P, Q, and E, Q, all divided by R. Where R, where R is equal to um, P. Well, okay, P is the origin, let's say. So P equals origin. P is at origin, and therefore, let's just delete this shit. Where R is equal to P E Y squared plus P X squared R squared. So then square root of that. Okay, cool. So that's that. And we have to just do that for, so that's the charge. And then we've got to do the gravitational part of it. I mean, that's it though, isn't it? So now I just need to break, is that it? If I've got the charge between the two, then if I've got the charge between the two, and I've got the mass above it, the gravitation. Well, I don't have the gravitation, so let's just do that as well. Gravitation is, so I summarize gravitational forces without denoting it, but this is plus that, so because that's obvious, we've already done the calculations, and then we have the P to N, the E to N, and I think that's it. So yeah, okay, so it is it. So then I need to go on subdivide this into the bits here. Yeah, so this will be, oh, what's a electron made of then? So electrons, quarks, and leptons. Quarks and electrons are the electrons are the smallest though. Okay, cool. So that's a bit easier. So we got E needs to go to P up 1, P up 2, and P down 1. So we got to go blue, green, and red. Okay, let's start with blue. Yksi, kaksi, kolme. Jeden. No, that's it. That's it. Oh, hang on though. Because these also will apply forces. Oh, nearly missed something there. So we got this. No way. No freaking way. This gets big. Because it's PU1 and 2, PU, PD1, N, PU2, PD1, P2, PU1, NU1, ND1, NU1, ND2. Okay, so there's more, and that is actually going to be this 2, 3, 4, 5, 6. So it's 6 to the power of 6. Is that correct? It's entity to the power of 6 times entity quantity. Therefore, 6 to the power of 6 equals 36 different forces are being applied here. Is that right? Let's count it up. It's a small number. So it's going to be 1, 2, 3, 4, 5 to the power of 5. And then you got, so it's 5 times 5. It's 5 times 6. It's 5 times 6. 5 times 6, yeah. It's not power 2, that's wrong. 5 times 6 equals 30. So it's 5, and then you've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're at 15. And then we've got the other side, 15, 30. 30 different gravitational forces. And then we got okay. Oh my god, there's so many. 5 times 6 gravitational forces. But then we got 1, 2, 1 times 2. So it's going to be 3 times 2. 3 times 2 equals coulombic. Sorry. 6 Coulombic forces. Oh, what a pain in the ass reality is. Is that right? One, two, three, 4, 5, 6. Must be, yeah. Yeah, that's right. And then we got this bad boy. So then we got, oi oi oi, 3 gravitational forces, and did I do that weirdly? How did I do that there? Oh, okay, I gave it more space. So let me just give this a bit more space. This will be 6 Coulombic forces. Anything else I've missed here? Let's see. I've done the gravitational force between the neutron and the proton. Now, the neutron has no charges, so we're just talking about gravitational from that point of view, but the neutron is divided into 3 subatomic particles. Subatomic particles. No, divided into quantum particles. So what are they called? Quantum periodic table. What? Angular momentum quantum number. Whatever. I don't care. Okay, yeah. So I guess I want quantum table. Table of quarks. Here we go. Up and down electron. Yep. Standard model of elementary particles. Okay. So we've got. So that's all the. So this divided into 3 different elementary particles. So fine. And that gives us a total of 30 gravitational, but only 6 Coulombic because there's only interactions between these, or repelling interactions between these. Okay. Is that it? It is it. That is it. That is it. And then we've got the piss at origin. Let's just make that P is at origin. So that's going to be the proton and the electron. Now that's interesting because there is a gravitational force, and the gravitational forces are going to be 6. No, that's wrong because electron is just one mass, right? So it is indeed 3 gravitational forces. But then you've got the gravitational force between these as well. Did I count that as well? I did. So it's going to be 3 times 3. Six plus 3, so it's 9. 9 gravitational forces. Let's just erase that. Let's just double check that. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 gravitational forces, and 1, 2, 3, 4, 5, 6. Sorry, it's going to be 3 times 2 plus 2 plus 3. 9. Okay. Also 9. Also 9. 9 plus 3. Yeah. Okay, that's correct, I think. Then I've got to do the interaction between the electron and the neutron, which is pretty much similar to 1. So it's 3, same as 1, but for electron. So it's going to be that. Oh, no, it's not. It's going to be E and N up 1, N down 1, N down 2. Is that correct? Yeah. So therefore, 1, 2, 3, these have no charge, but they will have a um, gravitational force. So it's going to be the same as this, i.e. 9. Yeah, I mean it is exactly the same as that, isn't it? So just delete that and then put that there. Because no, but I mean it can't have the kinetic forces. There can't be any, so there's literally none of those. So it's just gravitational forces. And so the sum total of all this, dear goodness me, go for this, is going to be 3948. Sorry, my math is really bad, so I better just do that properly. 9 plus 9 plus 30, 48. 48 gravitational plus 6, 9, 14 coulombic E P and then between 4 interactions of E P and N. Hey, that's not bad. That is not a bad bit of work there. I think I'd better recap this next time because it might be completely wrong. But I suppose what it means is I should probably make a model in a program. And it should, I'll do it in Unreal Engine. I think this is where we're going to start. That's my forces. And I'll just, as a diagram, draw the lines between those interactions. And we'll start from there. I don't know if you can see any of this, but yeah, this is forces between the neutron and the proton, the gravitational forces and coulombic forces between um, electron, and proton, and then forces between electron and neutron. That is it. Well, I'm going to call it a day there, I think. 2 hours 48 minutes. Might play a few games or watch some YouTube videos. That was fun though. That was fun. I like that. Next one's going to be really fun because I'm going to start plugging in this data into Unreal Engine. It's going to be slow because I'm crap at Unreal Engine. But there you go. Alright. Well, as always, keep loving, keep learning, and I shall speak to you all later.